This video is about thermochemical work. Now, there's lots of different kinds of work. There's mechanical work, there's electrical work, there's work against gravity. What we really want to talk about is something called pressure volume work. But let's talk about mechanical work for a minute first. This is a picture of mechanical work. The guy is pushing against gravity, so he is doing work. So the work is equal to the mass of that weight, the acceleration, how fast is he trying to lift that weight, and D, the distance in which he is lifting that weight. Okay, so that is work. If you take physics, this should look very familiar to you. But for us in chemistry, we tend to think about pressure volume work. Okay, so now if we're talking about pressure volume work, what we have are these pistons, frictionless pistons, which of course don't exist in the real world, but they simplify our problem. Frictionless pistons, and we've got ideal gases here underneath the frictionless pistons. So if the pressure of the gas under the piston is the same as the pressure, the atmospheric pressure pushing down on the piston, the system is at what they call equilibrium. There is no work being done. If the external pressure on the piston is less than the pressure from the gas, the pressure internal, then the ideal gas will push the piston up. All this space here will expand. Now the piston is performing work on its surroundings. The final volume will be greater than the initial volume. The work is done on the surroundings. If, on the other hand, the external pressure is greater than the internal pressure, the gas will be compressed and the work will be done on the system. Now remember this equation, the work is equal to the mass times the acceleration times the distance. Well, we can kind of rework that for my frictionless piston here. So work is equal to the external pressure times the cross-sectional area of the piston times the height, the change in height that it moves. And really, area times the change in height is really the change in volume. So work is equal to the external pressure times the change in volume. This is what's called PV work. So the units of work is joule. And you can look at this website and see how that's determined, but it's joule. And the R that we use for this has to be the R that has joules for a unit, joules per mole Kelvin. Instead of liters atmospheres per mole Kelvin, the 0.0821 that we're used to using, this R is 8.314 joules per mole Kelvin. So that's another R for you. Now, signs are very important for work. Whether work is defined as having a positive sign or a negative sign is a matter of convention. That is, we've all agreed this is the way it's going to be. Heat flow is defined as from a system to its surroundings is negative. Okay? Heat flow is defined from a system to its surroundings as negative, i.e., exothermic as a negative Q. Using that same sign convention, we define work done by the system on its surroundings as having a negative sign because it results in a transfer of energy from a system to its surroundings. So work done by a system on its surroundings is a negative sign because it results in a transfer of energy from the system to the surroundings. You won't always see that. Sometimes in engineering or something, you'll see it differently. But for now, for us, that's what it's going to be. So because delta V greater than 0 for an expansion, we actually have to put this little negative sign here in order to have the work done by the system be negative. So work equals negative pressure external times the change in volume. Now, we can talk about work and a chemical reaction. Let's say we have nitric acid here in this Erlenmeyer flask. There's our copper penny. We have a stopper here that's going to go into this flask. Notice there's a cord that goes from the stopper into this other vessel with a piston. Here's my reaction. Copper solid plus 4 moles of nitric acid goes to copper 2 nitrate plus water plus NO2 gas, 2 moles of NO2 gas. So we put the penny into the nitric acid, we plug the hole with our stopper, we get nitric acid, or nitrogen dioxide rather, gas, going into this, being formed in this beaker. So it goes out, it goes into this piston, or it goes into this vessel. We have pressure. The pressure raises the piston. Work has been done. Now, we can talk about the internal energy of a system. That is the symbol U. It's the sum of all the kinetic energy and the potential energy of all the components. Now, what we are calling Q when we do calorimetry reactions is really H. I'll get here in a second how H and Q are related, but let's talk about H for the minute. H is called enthalpy, E-N-T-H-A-L-P-Y, enthalpy. So that enthalpy of the system is U, the internal energy, plus the pressure volume work. And these are all state functions. Remember, state functions are things that don't depend on path. They don't depend on how you got there. They only depend on the beginning state and the end state. So, since we only care about a change, here's our old friend delta again. Remember, this triangle means delta, and delta means change. So, delta H is equal to delta U plus delta PV, which is really delta U plus P delta V, because we're talking about a constant pressure. Delta U, if you look in your book, is actually also equal to Q plus W. So we can say that this delta H is equal to delta U plus P delta V equals Q plus W minus W, because the P delta V is the minus W part. So look, delta H is indeed Q. But remember, Q and delta H are only the same at constant pressure. That's why they have that subscript P there. The subscript P is used to emphasize this only happens at constant pressure. So Q is really delta H at constant pressure. And if we're doing something on the bench top, we're doing something at constant pressure.